Okay, so for this session, basically what we're going to be doing is we're going to be going over like the chapter 7 basic integration rules. So in this chapter, we're going to be going over the integration rules that you guys probably learned but maybe forgot from Calculus AB. And then we're also going to be doing integration by parts and the tabular method, which is just another way to get integration by parts and get the answer. So this first problem, I split it up into 3 different sections. For the test, you guys will it won't be split up like this. So you guys are gonna have to recognize to use which method for a certain problem, and that's probably like the toughest thing to at least start a problem. Is to recognize which method you have to do. So I kind of like made a list, and I got this from class too, from what Miss Q said. But when you have any integral and you have like, because when you look at this, like you kind of need to know how to approach it and how to like tackle it. So if you follow these steps, and I promise that once you actually do like a lot of problems, like the steps come naturally and you don't have to go through each one. But at least if you're kind of starting out, it's good to follow them. So the first step I would do is to check the power rule. And I'll explain what that is just because I know that sometimes the math terms are a little ambiguous. So the power rule, if you guys remember, it's like when you have something like this and you're integrating that. The power rule is when you add 1 to the exponent and then divide by that number, right? So you guys are familiar with that, right?
Yeah.
Yeah, so that's the power rule essentially. That integral is not right at all, but just so you guys can visualize what that method is. And in order for that method to work, let's look at the first one, this integral. It's usually going to work when the exponent on the bottom is not to the 1, because if it is to the 1, think about it. If your exponent on the bottom is to the 1, when you bring it up, it becomes to the -1. And let's say this integral is not right at all, but let's say that we were going to do the power rule for this. If we were to do that, we would add 1 here and then divide by the number we get. And when you divide by 0, you know that you absolutely cannot do that. So that's why that wouldn't work. So at least with this first problem, I'm looking at it, just know that the power rule will probably not work if your integral on the bottom of like a fraction is to the 1. So for this one, I don't think the power rule would work. But then the second thing you can check is to see if you can use the ln rules. So that's the second step that I have here. Check the ln rules. And that's another form of integration that will work. And the way you know it'll work is if the derivative on the bottom is somewhere on the outside of this problem. Um, the derivative on the bottom of this, at least for number 1, it's 9 plus x squared. You want the derivative of that, d over dx. The derivative of that is simply 2x. So, this one, I don't think it would work. I want to show you guys how to do it, but as you guys can notice, for this particular problem, the 2x is there, but the -3 is also there. And since that's not the exact derivative, we can't just say that the integral of this is the ln rule, which is ln of 9 plus x squared plus c. That's why that one doesn't work. So that's not the answer. So that leads me to the third step, which is to check to see if it's an inverse trig function, which you guys all know as like arctangent, arcsecant, basically anything with an arc. Check inverse. That's the official name, the inverse trig function rules. So with these rules, at least, what I've noticed is that when you have an inverse trig integral, you'll notice that the top will have no x's whatsoever. And that's just like a certain thing that'll like be an indicator for me. Say like, oh, maybe I should use an inverse trig function rule for one of these. And I can explain why that works as I break up this problem. So, and then finally, if none of those rules seem to be working, you may want to try to see if you can use integration by parts or the tabular method, because those are they're not the most complicated methods, but those are like alternative methods to finding an answer that don't comply with the rules that we already know or the formulas that we already know. So that's when you would have to resort to that last step. And usually you can kind of skip through those three and know right away. But at least for this first problem, um, and since I categorize them by certain things, you guys are going to know that before you resort to integration by parts or the tabular method, you have to use one of these three first steps to find the answer. So it's definitely good to write these steps down, um, just so that you guys know what to do for the test tomorrow. And yeah, so do you guys have like the steps like written down or have an idea of what to do?
Yeah, I
Like
wrote
can I? Oh, okay. So let me clear and tell you guys how I did the first problem. So now that we know the steps, we just need to figure out what we can do. And I'm going to teach you guys like little tricks that I've kind of developed just from looking at the problem. So I'm looking at this here. The first thing that I always do is I check to see if the derivative here is somewhere in the problem. The derivative, and we had just kind of gone over this, but the derivative of 9 plus x squared is 2x. I see a 2x there. So I know that by manipulating this problem in one way, I might be able to use a rule that I know. But there's still a -3, and you can't just ignore that. If the derivative of this was 2x minus 3, then it would be a perfect ln rule, but we can't just resort to that. So let me erase this. So the first thing I'm gonna do, and let me know if like it ever gets unclear or you're confused as to why I did that, let me know just so that you guys aren't lost tomorrow. Um, the first thing I would do is just split this up, because the thing that I really want to focus on is the 2x, not the -3. So 2x over 9 plus x squared dx minus 3 over 9 plus x squared dx. Do you guys remember like that you can split the integral up like that and it's still the same thing?
Yeah, that was what I was thinking to do.
All right, yeah, that's the perfect first step. And now let's kind of like ignore this part over here. Ignore it, pretend the lines are there. Now you'll see that the derivative over here is actually what's there. It's just 2x. So that's the perfect time to use the ln rules. So we're going to integrate this one later. But you guys remember that for the ln rules, just the derivative on the top has to be the derivative of the bottom has to be in the problem. So since the derivative is 2x dx, we know that that'll work. So using the formula, we know that the integral of this is ln of the absolute value of 9 plus x squared. And then we still have to integrate the other one. And the reason why that works is because, the formula for an ln problem is the integral of 1 over u du is equal to ln of u plus c. Do you guys have the formula sheets from last year, like the integral rules? Because
No.
if not, like, wait, did you say yes or no?
No.
No. Okay, I'm gonna send them to you guys after this, just because they're super duper helpful. But just this is one of the important formulas that you need to know, and it's definitely useful to have them. So, do you guys understand at least the first one? Like, is that the answer you guys would have gotten if you had integrated that?
Yeah.
Yeah.
Okay, so now the second one. Um, Notice how the derivative again of the bottom is 2x, but what we have here is a 3 dx. More specifically, I'm gonna move the 3 on the outside just so that it's a little less convoluted. 9 plus x squared dx. So the derivative of the bottom, 9 plus x squared, is 2x. It's nowhere in the problem. So we know that it's not a power rule because this exponent over here said the 1, it's not going to work. And we also know that it's not an ln rule because we just did the ln rule for this one, and we know it has to have a 2x somewhere. So what's the next plausible formula that might work? If you guys remember the steps.
An inverse trig function.
Yeah, exactly. So yeah, I should have sent you guys like the formulas from beforehand, but I'm gonna write the formula for the arctangent one, and this is how it works. It's the integral of a squared plus u squared du is equal to 1 over a arctan of u over a plus c. And if you guys kind of look at the problem, wouldn't you say that this part over here kind of resembles this over here? Like, would you guys be able to make that connection like on the test?
Yeah.
Yeah. So I just looking at this problem, I knew right away that this would be an arctangent because the other ones involve a radical. So like for example, the one for arcsine is, let me do it in a different color just so that it's not as convoluted. It's the integral of 1 over a squared minus u squared du arcsine of u over a. And since this entire problem does not have a radical in it, I know that that's not the answer. Like arctangent was the easiest one to pick up on. So just a reminder of how to like put things in the formula, because it's really, really easy to do, because it's not like you actually have to integrate. It's just about identifying, hey, what's a, what's u, and then plugging it in over here. So let's figure that out. Ooh, let me kind of, I'm gonna do it in blue on the bottom. So whenever you have an arc type problem, I always just write I actually write it on the paper just so that it doesn't start confusing me. So I write what u squared and a squared are, and then I write what u and a are. So u squared, a squared, u, a. So let's identify those. Well, remember that remember this from calculus AB. U is like the longer version, while A is like just a number. So with that in mind, can one of you tell me what u squared is? You can just match it up with like the formula too.
X squared.
Yeah, u squared is x squared, so what's u?
X.
And then what's a squared?
3.
No,
9.
9. And what's a?
3, yeah.
3, yeah. So now that we have everything in place, it's actually really easy to just like plug things in. So I'm gonna continue writing the answer to this problem. I'll do it in green. So don't forget the ln of 9 plus x squared. One more thing, I'm gonna change this to parentheses instead of the absolute value, because it's always gonna be a positive answer, so you don't need the absolute value. The reason why that works is because for every answer you plug in, for every x value, it's going to be a positive number. So I'm replacing the absolute value to parentheses. Keep that in mind. I don't think it would mark your answer completely wrong, but it just makes it more correct. And then remember to keep the 3 on the outside. We moved it to the outside, so we're only integrating this. The 3 is separate from that. So now we're just going to use the formula over here. So it's 1 over a, which is 1 over 3, right? Arc tan of u over a. You said was x over a, which is 3, plus c. Remember that since this is an indefinite integral, there's no from 3 to 1. That's what it means. Since it's indefinite, we always have to add the plus c. So that is essentially the answer. The only other thing you could do is cancel these out, which just means that has a 1 in the front. So I'm gonna rewrite the final answer just because just for like peace of mind. But on your test, the right answer would be ln of 9 plus x squared in parentheses, not the absolute value. Again, leaving the absolute value would maybe take away like 1 point, but I know you guys want as many points as possible, so just keep that in mind. the 3 over here would cancel, so you're just left with minus arctan of x over 3 plus c. So hopefully that one made sense. I know that it's a lot. Oh yeah, say that again.
How do you know that like the 9 plus x squared is always going to be positive?
How do I know? Because the absolute value is just telling you that your answer needs to be positive.
Okay.
But like if this is always going to be positive, you don't need the absolute value. That's like what it's trying to say. Because when you think about the graph at least. 9 plus x squared. The y-intercept is 9 and it looks like this. It's always going to be above the x-axis, so it's always going to be positive. So whenever you plug in like -1, -2, 1, 2, your answer will always be positive because it's just always going up. And that's the logic behind that. It's a little harder to tell like when it's like, oh, like absolute value of e to the x plus 1 or something like that. Then I would say you might want to like graph it or kind of like see something like that. But for something like this, it's actually kind of easy to know that it's always going to be positive. So she might take, that's like 1 point away if you forget to do it. So it's not a super big deal. But yeah. Say it again.
No, that makes sense. What I said.
Oh yeah, I thought Caitlin said something.
I didn't.
All right.
No, I didn't.
Oh, it must have been background noise. So, yeah, that's the answer to that problem. I chose to do that problem because it involved ln rule and arctangent. So I thought it was like, a good practice for both rules. Yeah, so let me just, why am I erasing the whole thing? Okay, so let me go to the next one. So this is a different type of problem, I guess. But this one involves just other formulas. Okay, so for this one, it doesn't really involve like going through the steps. It just involves knowing like the formulas and also knowing how to manipulate. So these are the two like principles you need to know for this one. It's not really a problem you'd find in this chapter. It's just asking you to like recall the formulas that we learned from before. So the first thing that and maybe there's just like a force of habit that I know just from doing a lot of these problems, but the first thing that I did when I saw this problem was multiply by the conjugate. And I don't know if you guys remember what the conjugate is. So the conjugate is basically just like not an opposite, but like the conjugate, for example, of 1 minus sine of x is 1 plus sine of x. The conjugate for like 1 minus e to the x is 1 plus e to the x. So you're essentially just changing the sign. And the reason why we do that is because when you factor this out, for example, so let's factor out this one just because that's actually the one in our problem. When you do it, you get 1 plus sine of x minus sine of x. And the reason why we like multiplying by the conjugate is because these two terms cancel. And it's really helpful when, when by multiplying, you get like a trig identity or something like that. And I'll kind of go into that with this one. So when you finish multiplying this out, remember FOIL. I don't know what FOIL stands for, but yeah, you guys know how to do that. Sine of x squared, because it's negative sine of x plus sine of x minus. So we have 1 minus sine squared of x. So the reason why I did that is because this is a trig identity. And the purpose of doing this is because at this point in time, this particular integral, going back to the top, there's nothing you can do to split this up or like cancel things out. And the reason why is because the same, how we split up this one over here from before? We split it up like by doing 2x over 9 plus x squared minus 3, 9 plus x squared, and it's the same answer. That principle doesn't work over here. So let me just, whatever, I'll rewrite it. That doesn't work over here. You can't do 1 over 1 minus 1 over sine of x, because your denominator has to stay the same for each thing. But if for some reason this denominator became one term, then we could do that. So that if 1 minus sine of x, if we made that into, this is a made up problem. If it became 1 over cosine of x, let's say like that, then we could split it up. And then we can like use the integration. But that's the whole point of multiplying by the conjugate. It's just to make this bottom term 1. Does that kind of make sense?
Yeah.
Okay. I know it may not be like the first thing you guys like might resort to, but it's really, really, really important to know those trig identities. And I'm going to write them here just so you guys can remember them. So remember that sine of x, well, sine squared of x plus cosine squared of x is equal to 1. Another one is 1 plus tangent squared of x is equal to secant squared of x. And the last one, there are more, but at least for this particular these particular problems, 1 plus cotangent squared of x is equal to cosecant squared of x. I'm primarily relying on this one for this problem. So when you multiply by the conjugate, 1 minus sine of x, remember what you do to the bottom, you also have to do to the top. So when you do this, you multiply, you get 1 plus sine of x. And don't be concerned about the fact that we're actually making this one more convoluted by multiplying it by this. Because it doesn't matter how many terms you have at the top. The main concern is just having one term on the bottom so that we can split up the integral and go from there. So when you do this, we had done the FOIL for this, but this answer is 1 minus sine of x squared. And the reason why I did the conjugate is because I know that in this particular problem, this is already starting to look like one of these identities. And it actually is the first identity, just in a different form. 1 minus sine of x squared. If you, let me bring the identity down over here, is equal to 1. If you subtract by sine of x squared on both sides, you get that cosine squared of x is equal to 1 minus sine squared of x. That's exactly what we have over here, which means that this integral, let me not forget the dx, this integral is the same as 1 plus sine of x squared. You can't change the top, but the bottom is cosine squared of x. So that resolved our problem of having a denominator that we couldn't split up. Now that the denominator is just one term, we can split it up. So let's do that. Oh, sorry, erase the whole thing. So let me just erase a little bit of the bottom and then I'll continue working from the top. But when you split up this integral, you do it in blue, you can do it as 1 over cosine squared of x plus sine of x over cosine squared of x. So do not forget the dx's. You're going to get points taken off for that. So continuing the problem from the top of the page, when you do that, at least 1 over cosine squared of x. That's another trig identity. And I don't know if you guys remember what that's equal to. Just know that, here, let me try to go over it. Cosine of x is cosine of x, but 1 over cosine of x is equal to secant of x. It's like the inverse, or like the flip. It's the reciprocal, essentially. So another one, sine of x is equal to, sine of x is 1. 1 over sine of x is equal to cosecant of x. Yeah, I'm sorry, it does require you to know a lot of different trig identities, so it may be important to review those, but I promise that they're in your brain somewhere, so don't be too intimidated. And of course, tangent of x, when you flip that, which is sine of x over cosine of x, the opposite is cotangent of x, which is like that. So those are just important to know. But what we're focusing on is the one for this particular problem, which is, at least for this side of the problem, this is what we're looking at, 1 over cosine squared of x. Notice how it resembles this. 1 over cosine squared of x would just be secant squared of x, because really it's like there's adding a squared there, so the square would also have to be there too. So does that particular one kind of make sense so far? Like, do you guys kind of remember those identities or not really?
Yeah.
Yeah, I remember.
Okay, like that's really important. So bringing this work up back to the top, I can rewrite this as secant squared of x dx. And the reason why I want to do that is because that's actually a formula. Do you guys remember what the integral of that is?
No.
Do you guys remember what the derivative of tangent is? Or not really?
Not really.
Okay. The derivative of tangent is secant squared of x. You remember the mini quizzes where we had to write all the formulas? That's one of them. So the integral of this is just going back over here. So the integral of secant squared of x is tangent of x. Yeah, I know it's a lot. But now that we've done this term, we just have to worry about this one. But that's also another formula. We just have to fix it. So the first thing that I noticed, I kind of, when I was doing this problem, I split up the cosine because it's cosine squared of x. So I like did it in 2. So I just I kind of just I factored it out. So it's just cosine times cosine dx. And this can just be rewritten as 1 over cosine of x times sine over cosine of x. And the reason why I did that is because going back to those previous ones I had written, I know that, and let me just erase the bottom just because it's getting a little confusing. When you simplify these or rewrite them, I know that 1 over cosine of x is secant of x, and I know that sine over cosine of x is tangent. This is another formula. Again, you may not remember it, but when you go back to the formula sheet, you'll notice that the integral of secant of x tangent of x is just secant of x. And this just goes back to the derivatives that we had known from before. But yeah, the reason why this works is because the derivative of secant of x is secant tangent. And then obviously when you integrate, you go back. So that's why that's secant of x. And when you add plus c, that's your answer. So yeah, I know that it's kind of overwhelming. It's definitely a lot. I know that it's a lot only because it does take a lot of practice to know those trig identities because they're not that fun to remember. But I promise that when you finally remember them, it feels really great. So let's go to the next one. All right. I want to go over this one too because it's also another thing we learned back in AB. It's going to be a review of something called substitution, which is what we use, another way to integrate. There are lots of ways to integrate. It's just about kind of looking at the problem and seeing the best way. So for this one, I'll tell you why I use substitution for this one. And I don't know if you guys remember substitution, but it's like when we do let u equal something, we do du, the u's and stuff. That's basically what it is. But going back to here, and I'm sure that it'll ring a bell as soon as you see it. I'm gonna rewrite. I don't like having fractions, so I like to move things around so that it's not a fraction. So let me just bring this up. Negative 2/3 x dx. That's the first thing I always do, just to let you guys know. I hate when things are in fraction form, so I move things around so that it's a little bit easier. Okay, first thing. I'm looking at this integral. I know I could use the power rule right away if the derivative of the inside is on the outside. The derivative of the inside is 1. That's not here. There's an x. We can't do anything. I'm going to use substitution because substitution is a good way to integrate when you have like an extra term, essentially. So the extra term that we have here is x, because this problem could be easily done if the x was not there. But there is an x there, so we have to account for that. So let's use substitution. And tell me if this like kind of rings a bell. We say let u equal to usually like the bigger term, so x plus 6. We take du, and we know that du is equal to 1 dx. And the reason why we are doing these terms is because when you use substitution, it's like we're making the problem easier. So here, I'm gonna write the substituted form on the bottom. When we're using substitution, we're basically just plugging in these terms into our new problem. So we're saying that u is equal to x plus 6. So in our new problem, like quotation marks, new problem, it's the same problem, but we're just using simpler terms. We're letting u equal x plus 6. So u will go in here, right? We know that du is equal to dx. So we still have to account for this x, but dx is over here. We know that du is equal to dx. This becomes du. Now all we have to worry about is this term over here, the x. But we have that over here. All we have to do is subtract 6 from both sides, and we know that x is equal to u minus 6. So I can actually just plug in u minus 6 here, and this problem now becomes a lot easier. So basically what I'm going to do now is just distribute over here. So give me a second. Does this kind of make sense so far, guys? Or do you kind of not remember it from AB?
No, it's making sense so far.
Yeah.
Okay. So I'm going to distribute it and then integrate it that way. So u times negative 2 over 3 times u, which is really u to the 3 over 3, if that, because it's u to the 1, which is u to the 3 over 3. You guys know that when you're multiplying two terms with the same base and they have exponents, you just add the exponents. So this just becomes u to the 1 over 3. Now the other term is just minus 6 u to the negative 2 over 3. And this is all du. So I know that like at first it may not seem like it helped, but getting rid of that x essentially kind of removed our problem with the whole derivative. Now we can just integrate this like just straight off the bat. So again, I'm gonna erase the top so that it's not as convoluted. So you do it in green, but integrating this, now we have to split it up. I think it's easier to split it up just for like clarity's sake. Minus, I always move the coefficient to the front, negative 2 over 3 du. So when we integrate this, it's really just like the power rule. So what we do is we add 1 to the exponent, which is 4 over 3, and then we divide by that new exponent. So divided by 4 over 3. Minus 6, you add 1 to the exponent, which is 1 over 3. You divide by that exponent, 1 over 3. Remember, plus c. So now it's just about fixing it. So when we have this, this becomes 3/4 u to the 4 over 3 minus 6 times 3, 1 over 3. You flip it, becomes 3 to the 1/3 plus c. So this is really 3 over 4 u to the 4 over 3 minus 18 u to the 1 over 3 plus c. Finally, one last thing we have to do. Notice how the problem is in terms of x. So we already know what u is. In a previous step, we said the u was x plus 6. So now we just have to replace every single u that we have with x plus 6. I don't know if you guys remember that step. I always remember doing that. the final part we always do is just replace everything with the x's again. So it's x plus 6 to the 4 over 3 minus 18, x plus 6 to the 1/3 plus c. And that's the answer to that problem. So I wouldn't say that the hardest part of this problem is knowing how to like do the integrating. It's just about reviewing the steps of integration through substitution. So practice this method. Again, you guys know that I'll show you all the work that I do just so you guys can see it. And because I think that at least we'll see like maybe one type of problem like this on tomorrow's test because it's an important method that is from AB. So I'm not gonna do this one because I think it's a little bit easier. But I do suggest you do it for practice. I'll kind of set you guys up just because I want to do like the tabular method and integration by parts. That's the priority for this lesson. Really easy. Remember, the first thing I do is I hate fractions. So I always make it look like a multiplication problem instead of a fraction problem. I suggest you do the same. Remember the rule. If the derivative of the inside is on the outside, we're good to go. But if we have an extra x or an extra e to the x or an extra cosine or something like that, we have to use a different method. The derivative of this inside term is negative 2x. So all that we're missing here is negative 2. So we have to multiply by negative 1/2 on the outside. And then you guys can use the power rule and go from there. Do you guys remember how to do that type of integration? I don't think it's that hard. Guys, for number 4? Yeah, okay. Give me a second. Okay, so sorry. All right, number 5. Let's see what I put for number 5. All right. This is an arctangent problem, but it requires something known as integration by part. I mean, no, sorry. It requires something is known as completing the square. Do you guys want me to show it to you? Because it's kind of hard. Yeah. Okay. So the first thing, it's saying solve the differential equation. You guys remember these types of problems where I'm gonna do it in blue, where we would have to move the dx to the other side, because remember that when you're doing this type of problem, the dx already has to be there, and then you integrate. You guys remember that step from calculus AB where we would move the dx to the other side? Yeah. Okay, so now when you integrate this, we're left with y and this problem. So now is when I would tell you guys to look at the 4 steps that I wrote at the beginning of the problem of the lesson. So when you're looking at these, the reason why I told you is arctangent, because I've noticed that when there's really nothing at the top, there's no x, there's no x squared, there's nothing, it's usually an arc type of problem. And that's because when you look at the formula sheet, all those formulas usually just have like like a coefficient essentially at the top. But what you'll notice about this particular problem is that like we have our u squared, we have our a squared, but we have this extra thing over here. So the goal of this method called completing the square is to kind of fix it up so that we're left with something squared and then like an a squared. So completing the square. Completing the square is something, it's a method from algebra 1 and 2 to complete the square. So think about it like this. When you're completing the square, you're essentially trying to find like the missing term over here so that you can write it as like a polynomial and just be like, oh, x minus 3 squared. Your goal is to write it something like this, just so that it ends up being like a perfect binomial. So let's see. So for this one, I'm gonna ignore the plus 13 for now. To complete the square of this soon to be polynomial, you divide the middle term by 2 and then you square it. So it's -3 squared is equal to 9. You would add the 9 over here. And again, remember, completing the square is like an easy way to get like one of those little terms. So when you do this, you know that x minus 3 squared is equal to this. It's basically your guaranteed way of getting a polynomial that actually ends up being like a nice little factor, instead of having an ugly one, having to use the quadratic formula and something like that. So with this method, it gives us our u squared, because x minus 3 squared is a u squared. They're both squared, and the u would just be x minus 3, right? So notice how like it gives us like it kind of like it gives us the u squared. In a problem where we have an extra x term, it takes away the x term and it just gives us the u squared. But we have to make sure that we're following the right steps. So, and that's like the purpose of completing the square. So let me clear this and then continue. So I'm gonna complete this square within the problem, but that's just like a little background of what it's used for. So I'm gonna complete the square on the inside. So when I completed this square separate, sorry, those lines are not straight. X squared minus 6x, it was plus 9, right? We have the plus 13. Remember that when you're adding a term, we're adding a plus 9 that shouldn't be there. We also have to like balance it out. So I'm gonna do minus 9 too, because when you do plus 9, you need to have something to cancel it out, because we're adding like things there that really shouldn't be there. So the minus 9 will help balance that out. And notice how this is the exact same thing as what we've written over here. Because if we were to simplify this, these two would cancel out and you'd be left with that. So we're not changing the problem. By adding the minus 9, we've resolved that issue. But the reason why we need to add that plus 9 is because we need to complete the square. And that's what's going to give us our u squared. So this little term over here is going to help us with u squared. And the remainder is going to give us our a squared. And that's what we're going to be doing with the remainder of this problem. I told you that when you complete the square, it's literally giving you a perfect square right off the bat. So this term over here becomes x minus 3 squared. You guys should know how to factor that. It's x minus 3 times x minus 3, which is x minus 3 squared. And -9 plus 13 is plus 4. Now you'll notice that it's perfect for the arctangent formula. So have I lost you guys yet, or it kind of makes sense?
No, it makes sense.
Yeah, it makes
All
sense.
right, perfect. Okay. I know it's like a very atypical approach, like because you shouldn't. I mean, I guess you should expect to know algebra while you're doing calculus, but a lot of the problems in calculus require you to use those algebra techniques that we learned a long time ago, but it does really help. So now we know that this is clearly the u squared, this is clearly the a squared. So remember what I do. I like to write it on the bottom just so that I don't get confused. So u squared and u, a squared and a. U squared is x minus 3 squared. U is x minus 3. A squared is 4. A is equal to 2. And then remember that you always want to have the derivative of u somewhere in the problem, and du is equal to dx. So we have this checked off, we have this checked off, and since du is equal to dx, we have this checked off. So we're good. Now we can use the arctangent formula. And then that's the answer to the problem. So I'm going to erase the top so that we can plug it in. Do you guys remember the arctangent formula, or do you want me to write it again?
Can you write it?
Yeah. So the arctangent formula is the derivative of, give me a second. So I just want to make sure I'm writing the right notation. It's 1 over a arctan of u over a plus c. Oh, sorry. Oh my god, sorry. I'm messing up. So that's the formula for the arctangent. So it's the integral of 1 over a squared plus u squared du, and then it gives you that answer. So knowing that, we can now just plug it in. So I know that y is equal to 1 over a, which is 2. It's arctan of u over a, which is x minus 3 over 2 plus c. And that's the answer to this problem. So again, I know that it's kind of tricky, but again, with the practice, it really does make things clear. So yeah, did that method kind of make sense, guys? Or
Yeah.
yeah, I know it doesn't seem as hard like when you're looking at it, I guess, but when you're confronted with the problem, it can be like really intimidating when you don't know how to start it. That's like probably the scariest thing to do, like to not know how to start. Because once you know how to integrate, like it's kind of easy, but it's just about knowing where to start. So it's just about following those 4 different tips at the beginning of the video and then just continuing forward. It's almost 5, but I want to keep doing problems just because we haven't like hit the heart of like a lot of the problems that you guys are going to see. So yeah, I put a lot of problems, so I'm actually gonna just do a few. So yeah, I'll do the most important ones, I guess. So for integration by parts, this is your method when none of the 4 rules work, or when you have an integral where the formula is not there's no formula for it, so you have to use integration by parts. This is the perfect example because there's no formula for the integral of ln or of anything on the formula sheet. So we have to use integration by parts. So integration by parts. The most important thing to know for this, and I'm gonna get my notes just so that I can give you guys the right formula, but it requires you to kind of match things up. Kind of similar to like the arctangent ones where as long as we know what a and u are, we can put it by the formula. This is the importance of integration by parts. So with integration by parts, I keep saying integration by parts, sorry. With this, the formula is the integral of u dv is equal to, and u dv would be this, that's what it is equal to u times v minus the integral of v du. So again, it looks kind of convoluted at first, but as long as you start identifying the u's and v's in the right places, it becomes not too bad. So a little tip for how I do it. You always start with a u over here. Actually, wait. You always start with the problem, of course. So let me write that. The problem is ln of x cubed dx. When I'm identifying what the u's and v's are, I always like to keep something in mind. So we start with u, we start with dv, because that's the root of this formula. You always want your u to be something that you can easily take the derivative of, and you always want your dv to be something you can easily take the integral of. Because part of the problem, notice how this has a v and this has a du, which are not in the original problem. From dv, we need to get to v, which is integration. From u, we need to get to du, which is derivation or taking the derivative. So I want to make sure that u is an easy derivative. I want to make sure that dv is an easy integral, because let's say that I put ln of x cubed is the dv. I have no idea how to take the derivative of that because there's no formula for that. That's not easy. So it's kind of obvious to go for ln of x cubed as our u, because there is an easy formula for that. You guys remember that the integral, the derivative of ln, any ln, is 1 over the term over here, which is x cubed, times the derivative of the term, which is 3x squared. And don't forget the dx. So that's like the formula for that, and that was an easy derivative, at least. So we know that this is not going to be our dv. We already said that ln of x cubed was our u. So the only thing left is dx. So dx has to be that. The integral of dx is really easy. It's just x. Remember that there's a 1 here. So when you take the integral, you're left with x. So that's really what it is. Does that make sense so far?
Yeah.
Yeah.
Okay. So, and you guys remember how to do the integral of an ln problem. I mean, sorry. You guys remember how to do the derivative of an ln problem, right?
Yeah.
Okay, yeah, that's an important formula. Again, I'm gonna send you guys all the formula sheets, but that's an easy one to remember. It just kind of requires the remembering. I forgot it, of course, but as soon as I remembered, I was like, yeah, I remember doing that last year. So now, and that's why I kind of like integration by parts, because it's just about matching things up with the formula, which I did write at the top. So keep this in mind as we write it. So the integral of ln of x cubed dx is u times v. U is ln of x cubed. V is x minus, remember the minus, the integral of v, which is x, du. This is all of du. So we're going to write it. 1 over x cubed 3x squared dx. So let's start simplifying. I'm going to do it in black again. I always like to move the x to the front of the problem. So I'm going to move that there. Minus, let's see what we can cancel over here. The x cubed and the x squared can cancel. So you're left with an x here. And you're left, wait, give me a second. I think I messed something up based on the work that I'm doing. So give me 1 second, because of course I don't want to be telling you guys the wrong thing. Actually, no, I didn't mess anything up. Okay, so this cancels out, and then notice how we have an x here and an x there. So those cancel out. So all that's left is a 3 on the inside, and that's really easy to integrate. Thank God. So I'm gonna erase this and integrate. So what you're left with is x times ln of x cubed minus 3x plus c. And really, that's the answer to this problem. So did this kind of make sense?
Yeah.
Okay, yeah. So I'm gonna also teach you just some tricks based on the formula sheets, just in case. No, this would be marked right on the AP test, but just a reminder, when you have an ln problem and it has an exponent, you can rewrite that problem as having a coefficient of 3. So just keep that in mind. So another way of having this answer would just be 3 of x, ln of x minus 3x. This is important for the multiple choice section of the AP test because they may not have this answer as one of the choices. So you would need to know, hey, like I can actually bring down this exponent, make it a coefficient, and rewrite this answer. So both are right. I encourage you to practice using both, but just keep that in mind because I remember doing multiple choice practices last year, and they definitely would do that. They would have a choice that was slightly different from your answer, and you want to make sure you get that because you did all the work to get the answer. And then you look and none of the answer choices are what you got. You have to manipulate, and you want to make sure you put the right one instead of guessing or actually getting it wrong. So just keep that in mind. Yeah. So yeah. I want to do a problem like this because it's interesting. And then we're gonna move to the tabular method because actually those are really easy, so I like those. But we need to do integration by parts too because that's definitely your last resort. Know that for these problems, integration by parts will work for all of them. So I'm gonna scroll to the bottom to the tabular section I did. Integration by parts will work for all three of these, but um, use the tabular method when it's just a little bit easier. But the tabular method won't work for every single problem. So just keep that in mind. Your first, again, I always like to do like a little checklist. So when you're faced with these problems, check to see if tabular works. If tabular doesn't work, go to integration by parts. And I'll show you how to check for tabular, but let's do this one first. So the integral of arcsine of t dt. First thing we do, we have to figure out what u is. We have to figure out what dv is. Do you guys want to take a guess at what they are? Kate or Natalie?
Would u be arcsine of t and dv would be dt?
Yep, exactly. And the reason why, this is an easy one. The reason why is because there's no formula for the integral of arcsine. So we can't have it as dv because we can't integrate arcsine of t. Think about it. If we made dv arcsine of t, dv would be literally what the problem is, arcsine whatever. So it can't be that. I know that don't get confused. One of the integral formulas has an arcsine as the answer, but none of the integral formulas have an arcsine in the actual integral. So just keep that in mind. Yeah, so u is arcsine of t, dv is dt. This one's easy. When you integrate it, you get t. Now you still have to remember the formula for arcsine of t, which I will write just because it's a little bit I know that we kind of look over the formulas before we take a test because we don't remember all of them. Remember that the derivative of arcsine, so arcsine of u, is 1 over the square root of 1 minus u squared du. So for this particular problem, the derivative of arcsine of t is 1 minus the square root of 1 minus t squared dt. That's it. So let me erase this and actually start integrating. So using integration by parts, we know that arcsine of t, the integral of arcsine of t dt is equal to, remember, u times v, so these two, arcsine of t times t, minus the integral of v times du. So it's always this first and then this first. Maybe like doing those lines will help you figure out what to do in place, just because you can have the formula in front of you in front of the AP test, of course. So it's v times du. Oh, sorry, I actually wrote v. V is t, and du is 1 over 1 minus t squared dt. So this is easy. Remember, I always like to write the letter in front of the longer term, so I write it as t times arcsine. Give me 1 second. It's a little bit confusing for me to see, and if it's confusing for me and I'm writing it, I just want to make sure that you guys are seeing it clearly. So this, I'm gonna write the equal sign over here so that there's more room. It's t times arcsine of t. And this integral is t over 1 minus t squared dt. So this term, we're good. We don't have to do anything with it. It's t times arcsine of t. But we have to integrate this, and that's going to be how we get our answer. This integral is actually kind of easy. Do you guys know which rule you guys would use for this? Do you want to take a guess? Okay. The first thing I would do, remember, I hate fractions. I don't hate fractions. I just hate because they make things a little bit harder to see. So change that fraction. Get rid of the fraction. Rewrite this as 1 minus t squared to the negative 1/2 because that's a radical. So it's really to the negative. It's really to the 1/2. But when we bring it up, it's the negative 1/2 times t dt. Now, do you guys see which method we can use to integrate it?
Isn't this, wouldn't we have to get the derivative outside, so multiply by -2?
Exactly. So this is the power rule. I mean, yeah, this is the power rule because we need to have the derivative of the inside on the outside. The derivative of the inside is -2t, so we just need a -2 over here. Remember, what we do the inside, we have to do the outside too. So we have to have, sorry, I didn't give myself enough room. We have to have a -1/2 on the outside too to kind of cancel out what we're adding or multiplying to the problem. So now that the derivative is on the outside, we can use the power rule. So t arc sine of t plus 1/2. And yeah, now we can use the power rule. So we do 1 minus t squared plus 1. So the exponent now becomes 1/2 divided by 1/2 plus c. Divided by 1/2 is really just multiplying by 2. So when you rewrite this, this just becomes, I'm not gonna rewrite that. This becomes 1/2 times 2, 1 minus t squared to the 1/2 plus c. So the final answer, now I'll write, sorry. The final answer is t arc sine of t. These two cancel. So what you're left with, ignore that. You're left with a radical 1 minus t squared plus c. And that's actually the answer to this problem. Again, I know it's really, all those terms are a lot to process, but again, it's just about practicing and kind of going back to those rules that we are doing, because while doing integration by parts, we had to use one of the 4 steps that I had showed you at the beginning, because we had to recognize that this integral over here, let me do it in blue, the one at the top, the one at the top, we had to use the power rule to integrate that. So it's just about recognizing that. Yeah, so hopefully that made sense, but this one is not going to be too bad if you guys do it. This one too. I want to do this one as our last integration by parts problem. So let's just do it really quickly. So because the other 2 that I had there are kind of tricky, but they use the same methods as before. So let's do this one. Remember the first thing we do for integration by parts. Let u equal this, let dv equal that. So what's u? What do you guys think u is, and what's dv?
Cosine of L in the rect, and then v dx.
Yeah, perfect. So that means we know that v is x, du. The derivative of cosine of x is negative sine of x. Let me go back to the formula sheet just so you guys remember what to do. So I'm gonna send you guys the formula sheet for the derivatives and the integrals because those are important. But know that the derivative of cosine of u is equal to negative sine of u du. So the derivative of cosine of ln of x is negative sine of ln of x du. Remember, we have to do the derivative of the inside. So it's 1 of x dx. 1 over x dx. So remember that. This kind of goes back to like the chain rule where we have to keep taking the derivative of the inside. And that just goes back to this. You know, it's not just negative sine of x ln of x. You have to do the inside too. Unless the inside is x, then it would not be necessary. But since it's not, you have to remember the 1 of x dx. So this is negative sine of ln of x 1 over x dx. Okay. So now back to putting it into the formula with the integration by parts. So different color just to change it up. Sorry, I keep unfreezing the screen. So cosine of x, the integral of cosine of ln of x dx is u times v, which is x times cosine of ln of x minus the integral of it's the integral of x times du. So x times negative sine of ln of x 1 over x dx. A lot of x's. So at this point, I would say that you have to okay, so I don't know if you guys remember this from class, but sometimes you actually have to do the rule twice. So you have to do integration by parts twice in order to get the answer. So, and that's what you actually have to do for this particular problem, because when you simplify this out, you'll actually notice that this little formula over here is, here, let me write it out. Sorry, to erase. So this formula, x cosine of ln of x minus, these x's cancel out, and I'm going to move the negative to the front, so this becomes a positive. Sine of ln of x dx. Notice how, like, even though it's not the right integral, it's kind of where we started. It's like the same concept, except the sine is now cosine. And there's no formula for that, so we can't integrate it right after that. We have to use integration by parts within the problem. So that's why this is a good problem to do, because it's good to practice it having to do it twice in the same problem. So with this particular problem, I'm gonna make new u's and new v's. It's really the same thing essentially. So this is cosine of ln of x times 1 over x dx. V is just x. So just keep that in mind. Remember the formula. We're doing the formula within the formula. So keep that in mind. Plus u times v, which is x sine of ln of x. Oh, sorry, I'm writing this really bad. And then of course we have to do minus the integral. Minus the integral of u times v times du, which is x times cosine of ln of x 1 over x dx. A lot. Really, really, really important to know. This term now, and what I'm gonna do is, let me just give myself more space to write it. Cosine, make sure you guys are there just because this is important. So we have x cosine of ln of x plus x sine of ln of x minus, these x's cancel out, so we're left with cosine of ln of x dx. Notice how this is the exact same thing as this. So what Miss Q told us in class was that if those are the same term and we're trying to solve for it, what we can do is just move this to the other side. And when you move it to the other side, what we have now is 2 cosine of ln of x dx, which is x, and you leave everything else from the other side. So you have x cosine of ln of x plus x sine of ln of x plus c. There are no more integral signs, so remember to add the plus c. There's one more thing we have to do to this problem. Remember, we're solving for the integral of cosine ln of x. We use the 2 because the 2 made it easier for us to get rid of that term, but there's still a 2 there. We need to get rid of it. So what would we have to do to get rid of the 2 on that side?
I don't know.
Just divide by 2, right?
Yeah.
Yeah, that's all we have to do. So when you divide by 2, I'll do it in blue. You're really just you're dividing by 2, which is just multiplying by 1/2 for each term. And that's the answer. Let me just keep writing it. But yeah, I know it requires a lot of steps, but so you add a 1/2 to the x cosine of ln of x, you add a 1/2 to the x sine of ln of x, and c is going to be a constant either way, so you don't have to do 1/2 c, it's just c. So that's the answer. Again, really convoluted, but you have to know it for the test. Yeah, so that's the last integration by parts problem I'll do for today. I want to do 2 tabular problems. They're really easy. So do you guys know how to do tabular or not really?
No, not at all.
Not at all? Okay. I promise it's really easy. So tabular. You can only use tabular if one of the terms you have here will become 0 if you keep taking the derivative. And the other term you can use, you can just integrate it. The reason why. For tabular, basically what you're doing is you're going to keep integrating this column, and you're going to keep taking the derivative of this column. So you want to make sure you can keep integrating this part until you get 0. You may want to make sure that you can keep integrating this part. Let's say that the problem was x squared ln of x dx. We can do this because we can do x squared, take the derivative, 2x, take the derivative, 2, we get 0. But what's the integral of n of x? We can't do it. There's no formula for that. That would require us to use integration by parts, which is redundant. But for this particular problem, we can do it because if we keep taking the derivative of this column, we get 2x, we get 2, and then we get 0, right? We hit 0, so we're good. We stop. For this, we can do the integral. So remember, this is deriv, this is integral. The integral of cosine of x is give me a second. Isn't it sine of x? So yeah, it is sine of x. So the integral of cosine of x would be sine of x. Let me just get my work just so I can make sure that I'm following the right steps. Because again, I don't want to be telling you guys the wrong thing just for you guys to get confused, I guess. So where's this problem? I found it. Yeah. So the integral over here would be sine of x. The integral of sine of x is negative cosine of x, and the integral of negative cosine of x is negative sine of x. So for tabular, 2 more things you have to do. You have to remember to do plus minus, because each row is like a different sign. So this is plus, minus, plus, minus, plus, minus. And your answer, you get your answer by multiplying from like across different rows. So you multiply these 2, remembering this sign. You multiply these 2, remembering this sign. And you multiply these 2, remembering this sign. There's no 0. There's no term that goes with 0, so there's nothing you do. So the answer, how does it make sense so far, guys, or not really?
Yeah, it does. I kind of remember this from class.
Okay, Yeah, it's really, really easy to do it, and I promise it saves you that annoying like step of having to do like these and the d's and stuff like that. So now it's just multiplying. So x squared times sine of x is x squared sine of x, and it's a plus, so we keep it positive. 2x times negative cosine of x is negative 2x cosine of x. Remember the negative, so it actually becomes 2x positive 2x cosine of x. The last one, 2 times negative sine of x, we leave it positive, so it just stays as negative 2 sine of x plus c, and that's the answer. Notice how it was much quicker than having to do the integration by parts. So really try to practice this method because you need to use it as many times as you can because it saves so much work. It's a lifesaver. So just keep that in mind. Yeah, say that again.
Start with a positive.
What?
It always starts with a positive, right? For the signs.
It always starts with a positive. It's always plus minus plus minus plus. Like always go with that pattern, and it's always cross multiply, cross multiply, cross multiply, and it's always derivative, 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 and then integral, 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 integral. That's why I like it. It's just always the same thing. Just remember that you can't use the method unless one term will eventually let you hit 0. 0 is your mark because it lets you stop. If not, it'll be going infinitely, and that's redundant. And you need to know that you can just integrate, integrate, integrate. So it needs to be an easy integral. So how will we do the next one? I'll let you guys do the next one, and then we'll stop. So this one. And this one does work. So how about we start? So complete, remember the derivative. You don't have to write the name like derivative, integral. I just do that just so you guys can know what each column is doing. So how would you complete the derivative row?
The same way as last time, so 2x, then 2, then 0.
Right? And then how would you complete the integral row?
For the integral of e's, is it just moving the 3 over and then doing 3e to 3x for the next one?
Say that again.
For integral, is it just moving the 3 over and then doing 3e to the 3x?
3e to the 3x. I don't know what you're saying, so I'm gonna actually write out how to do it. The integral of e to the 3x, remember, this term has to be on the inside. It's not, so we had to add a 3 here, so it has to be a 1, 3 here. So now the integral of this is this. That's the integral of e to the 3x. You don't have to do that on the side, but you can do it to the side if you want. That's an easy one to do. Just know that you're always, whenever you integrate this, you're always missing a 3 on the inside, so you always have to have a 1/3 on the outside to cancel it. So you're really just multiplying by 1/3 for each integral. So the next one is 1/3 e to the 3x. The next one is 1/9 e to the 3x. The last one is 1/27 e to the 3x. And stop. Once you have a 0, you stop there. Remember, we do plus minus plus minus. Remember, we cross multiply. So we do this term. This one goes with that one goes with that, and that one goes with that. And now it's just about writing the answer. So the integral of this x squared e to the 3x dx is equal to, you guys tell me the answer. What is it? Start. Like go term by term and tell me.
How would we like
1/3 x squared e to the 3x.
Exactly. And Ali, what was your question?
No, that's what I was wondering. Like, do we put the 1/3 in the front?
It doesn't matter, but this is how I always picture it. The coefficient kind of goes first, your x goes second, and then the most complicated thing goes last. So the ln would go last, the e would go last, the cosine would go last. That's how it usually works. Okay, so what's the next one? Or yeah, what is it?
Minus 2/9x e to the 3x.
Perfect. Last one.
plus 2 over 27 e to the 3x
What's one more thing you have to add?
plus c.
Yeah, perfect. And that's the answer. Notice how that it's like much easier to do than the integration by parts. So again, use it as much as possible. And yeah, I know we didn't get to do every single problem from this mini review that I made, but hopefully it did help. And yeah, I'm gonna stop the recording.